Hello everyone and welcome back to another video. In today's episode we're going to be discussing intermolecular forces and their applications across multiple fields of chemistry. Let's get right into it. So we see intermolecular forces in play across our daily lives, from boiling water to gasoline to even in the chemistry lab and salt. Now, bonding is something you went over in general chemistry, but I'm briefly going to discuss it. This chart is essential in your understanding of bonding in terms of electrons, whether they're completely transferred, as in the case of ionic bonds, or unequal sharing, polar covalent bonds, or equal sharing, which is the case of non-polar covalent bonds. More scientifically, this has to do with electronegativity differences, and we see this with nonpolar being less than 0.5. Polar covalent bonds are in between 0.5 and 1.6, and ionic greater than 2. So an example of an ionic bond and how we determine it is simply looking at the electronegativity values of the two species involved, so sodium and bromine, and then calculating the difference between the two values. In this case, it's 1.9, which will place it in an ionic bond. In general chemistry and organic chemistry, we refer to these intermolecular forces as simply being intermolecular forces. But if you get to the level of biochemistry and above, we like to refer to them as non-covalent interactions, because we'll see not just species or molecules interacting between one another, but we'll see whole regions of a protein interacting with one another due to those intermolecular forces. And so this brings us to our very first interaction. Throughout this video, we'll refer to them as just intermolecular forces or interactions. But the first one here is the ion-ion. When in a crystalline solid, the lattice energy actually makes us stronger than a covalent bond, which is extremely interesting, as we see with table salt, sodium chloride. However, in biochemistry, when looking at different regions of a molecule, we say maybe the C-terminus and the N-terminus interacting in different regions of the polypeptide, we refer to this as a salt bridge. That is not displayed here, however. The second interaction we're going to look at is the ion dipole, and this is seen in solvation. When you would place, for example, in the laboratory, putting sodium chloride into a water solvent. And it's also responsible for So in your biology classes, these ion channels are extremely important with action potentials and all other kinds of transmembrane transport. The next one is dipole-dipole. Now, this occurs when adjacent dipoles interact. Now, when we looked at that previous chart, the bonding chart, we see that dipoles arise upon unequal sharing of electrons. And this all comes back to those electronegativity values. So in this case, obviously chlorine is more electronegative than hydrogen, slightly. I think it's maybe, actually, don't quote me on it, but I'm not sure. As we see here, chlorine is obviously more electronegative than hydrogen, so that's going to hold the partial negative charge, whereas hydrogen holds the partial positive because the electron density is being shifted towards the chlorine atom. And so in solution, these can interact with one another because they are those partial positive and negative charges. Partial positives and partial negatives interact with one another. Now, a special case of this dipole-dipole, and it's quite honestly stronger than normal dipole-dipole, is hydrogen bonding. Now, the most clear example of this is water interacting with other water molecules, but the main hydrogen donors and hydrogen bond acceptors have to deal with oxygen, nitrogen, fluorine whenever they're bonded to a hydrogen. And so in this case, these are the donors, and the individual electronegative atoms, the oxygen, the nitrogen, the fluorine, those are the acceptors. So from our physics knowledge, we know that positives and negatives interact very well together. And so when we have these partial negatives and the positives, they'll interact, and that's where our hydrogen bonding occurs. Now this is just a little display of hydrogen bonding in solution, just water molecules. One more very interesting interaction that you'll see in biochemistry is the cation-pi interaction. And so we know with our knowledge of benzene rings that they exist really as electron clouds above and below the entire ring. That's known as a quadrupole. With this in mind, we know that this top part of the ring is partially negative, and this bottom part of the ring is partially negative as well. So, with this in mind, this can interact with a positive charge nearby. This plays a large role in protein folding, and here's just another electron diagram of electron density. This is just a diagram showing the partial movement of pi electrons. Another interaction that's seen across all molecules and is the weakest of the interactions is the van der Waals, also known as the London dispersion forces. A little bit more accurate of a description, London dispersion, because this arises from instantaneous dipoles. So at any instant, a molecule can partially shift its electrons, therefore inducing a partial shift in electron movement in another nearby molecule. This, like a battery, partial positive and negative charges, they interact with one another. So this negative is going to interact with the positive, and it's just going to keep on going, forming more instantaneous dipoles and induced dipoles. We see this with long hydrophobic chains, since this is the only interaction that they undergo. So at any instant, this portion of the molecule could become partially negative, this portion of the molecule could become partially positive, and therefore they'd interact with one another. And one less interesting force that is not discussed very often is the hydrophobic force, also known as the hydrophobic defect. This is clearly displayed anytime you would mix something like water with oil. They simply do not interact. And what is happening is the nonpolar molecules are aggregating together and excluding the water molecules. Now, this isn't just a force to forget about. This force actually plays a large role in globular protein folding. And so when you get to those higher level biochemistry classes, this is definitely something that's going to be applied. So I hope you enjoyed this quick little brief description of intermolecular forces. You can apply this to your general chemistry classes, your orgo classes, and your biochemistry classes. Use this video as review or use it as your initial learning prior to class. I hope you enjoyed. We'll see you in the next one. Thank you for watching.